Hi everyone. In a power system, there should always be a balance between generation and consumption. Let's have a look at how this is done. In traditional power systems, the active power balance is controlled by generators. When losses are neglected, the active power balance can be expressed as the equation shown in the screen. The mechanical power supplied to the generator accessed by the primer mover is equal to the electric active power, which is the output of the generator, plus the power accelerating or slowing down the generator. When the generated power and consumed power are in balance, then the mechanical power and the electric active power are equal, and there is no accelerating power. Let's analyze what happens when a change occurs in the system. When a sudden increase of active power consumption of the load occurs and the mechanical power supplied to the generator remains constant, a decelerating power arises. When a decelerating power arises, it means that the rotation of the generator slows down and the frequency of the electric power output drops. In a traditional power system, a centrifugal governor controls the speed of a machine by regulating the amount of the fuel that is supplied to it. In this way, a near constant speed, independent of the load, can be achieved. In the case of a steam engines, the governor regulates the admission of steam into the cylinder, as you can observe in the illustration. It is important to mention that frequency is a common parameter throughout the network. An increase of active power consumption at a certain load point results in a reduction of the frequency in the whole system. The active power balance is restored by the speed governor. This action is called primary control. The speed governor can be set with a frequency power characteristic in order to do so. The frequency power characteristic or droop has a negative slope and is expressed as follows. Droop is the frequency drop in per unit of the rated frequency when the active power output of the generator rises from no load to full load. The droop characteristic shown graphically in your screen. As you can observe, the power increases as the frequency decreases. For multi-generator system, the network power frequency characteristic given by lambda is determined by the droop of the primary active power controls and the nominal rated power of all generators in the system. In such a case, a change in active power consumption is met by all generators in the system, given as the combination of all droops as shown in the equation. The network power frequency characteristic lambda can be written as the negative of the change of power in the system, divided by the change in frequency of the system. After primary control takes place, the power balance is restored at a lower or higher frequency, which is not a desirable operation condition. Secondary control brings back the system to the original frequency by increasing temporarily the prime mover power that raises the kinetic energy, and therefore the frequency of the generating unit. It also allows to bring the tie line exchange of power back to the one that was agreed between the areas. An area can be a country, for example. In the figure, you can observe how the secondary control is used to modify the setting of the speed governor in such a way that the frequency is brought back to the original reference. There is another control mechanism that operates in traditional power systems. However, this control works under a large time frame, generally under a horizon of 24 hours. This control is known as the tertiary control. Tertiary control is used to operate the power system in the most economical way. This is done using optimization algorithms that takes into account the cost of operation of the different generation units, their startup and shutdown cost, and estimation of the demand curve, among other information. The optimization routines determine which units should be turned on or off and provide the optimal way in which the available generation units should dispatch their power. Today, you learned about the basics of a traditional primary, secondary, and tertiary control. In part 2 of this lecture, you will learn about the influence of renewable energy sources in the application of control, and you will be introduced to the control mechanisms used in microgrid.